Hello everyone. We are studying the high-level assembler language of IBM Z systems. We had a class 1 where we had introduction about the mainframe assembler, which is also called HLASM. And today we are into class 2 where we are mostly talking about how do we handle integers. So what we have learned in the class 1. Let's quickly recap. HLASM, high level assembler language. Why we're calling it high level? Because many people think that assembler language means it can be directly executed. It cannot be executed. You have to still compile it. You will get an object code. You have to still link it. You get what is the equivalent of a load module, and only the load module can be executed. So that's why we are calling it high level assembler language. Then how memory is organized. We studied about it. What is a bit and a byte? What is a half word, full word, double word, etc. Basically, this is how the memory is organized. How registers are organized, we studied. There are 16 general purpose registers, which is of most significance to us. There are other IO registers and some other registers are there, which we are not going to get into, but we briefly got introduced to them. How the registers which are sitting in CPU and the memory or storage in our language, everyday language, call it RAM and ROM, how they interact is also something we spend some time on. How various types of variables are defined and how they are stored. We also learned that irrespective of whatever you call it in your program, ultimately the data is stored in bits and bytes, and we read it in a hexadecimal format for our easy understanding. When something goes into the GOS system mainframe storage, it doesn't know where it is coming from. It is a character, is it a number, is it a decimal number? It doesn't know anything of it. It's just going and storing the values as it is. Everything is depending on the interpretation. We studied a little bit about the PSW. What is a PSW? Program state word. This is a 128-bit register sitting in the CPU. At any point of time, it gives you the status of the program. That's what we studied. This can be very, very useful when you're doing the debugging. When a program happens, first thing we can go and see is what is stored in the registers and what is stored in the PSW, which will give a very good understanding of where we are in the program. We also looked at a sample program. I didn't call it even a sample program, a small snippet of the code, and we are going to use the same small snippet of the code and we keep expanding it over a period of time in our rest of the classes or rest of the training material. So this is what we looked at. In our next slide, let us spend some more time on understanding the variables, how they are defined. Let us spend one more time. So let's look into introduction to the variables. DC is a defined constant. That's how we define a variable. Just think for a minute. When we say define constant, we are not using a constant in a regular sense like a Java program or a Python program where you have a constant and the variable value will not change anywhere. It will remain constant in a COBOL programming also. Here, all we are saying is that it is a variable and it has a value initialized num1 dcf100. That means the num1, which is a variable name, is initialized with a value of 100 and it is a full word. So three things we are telling. It is a full word, it has an initial value and the name of the variable itself, which is num1. Similarly, str1, which is a string 1, defining a constant here or defining a variable. It is a character and its initial value is a b c. Okay, then we are going with ds. What is a ds? Here we are just reserving a storage, but we are not doing any initialization. Why do we do it? You have seen in COBOL, we have a group variable and there will be variables below that. So each of those variables may be having some initial value and certain different, let us say emp underscore data, which is having a emp num and employee name and say employee gender, date of birth, things like that. Similarly, we have a group variable there. Here it is more or less like that. We are using a DS most of the times. Say report DSCL80. What will you do? You blank the entire report, right? And then you start populating the report record with various values. So what are the various types of variables? H half word, we have done this 2 bytes. F is a full word. X is a hexadecimal. When you say X, it's just a one character. Sorry, hex is a hexadecimal, and C is a character string, which is just a one variable. Then B is just one byte, and P as a packet decimal. Packet decimal is a very complex subject. We will handle it later. When you want to have hexadecimal with a length n, you do XLN, and we do a character with a length n, you do a CLN. These are the various types of variables you keep seeing continuously. In this particular example, you have seen F100, which is a full word, initial value 100. CABC, that character string is having length of 3 because you have defined it as a ABC, whereas report DS is CL80. So you have already defined the length. CLN80 you defined. So the variable report is of length 80, but it is not initialized any particular value. Hope this is clear. Let's move on. So let us look at how do we handle these integers. We have defined four variables here: num1, num2, num3, and a result. And if you look at the first one, num1, DCF5, that means it is a full word with an initial value of 5. Second one, num2, is a half word with an initial value of 100. And num3 is a double word with an initial value of 200. You know, half word is 2 bytes, full word is 4 bytes, and double word is a 8 bytes, and we are initializing these variables with these values. The value 200 can be stored in half word and full word also, but for us to understand how these various combinations work, we are going this way. We are defining three different variables with three different lengths: full word, half word, and a double word. Then we are also defining a variable called result. We are calling it as a full word. That means it is 4 bytes, and it is not initialized, so it might be having a garbage from the previous program, or somewhere something would have been stored. We are not cleaning up that place. Now let us look at the first instruction: load num1 LR1 num1. Load num1 is its label. What do we use the label for? In case you want to do a loop, or if you want to come back after certain conditions, we come back here and we use the load num1 as the label. L stands for loading R1 num1. So num1, which is a full word, it is getting stored in the register R1. So L is what it is doing. It is loading a full word. Please note there is nothing called LF. Now AH, what is they doing? We are adding a half word. What is this half word here? Num2. So R1 is getting added. Num2 is getting added to R1. R1 is the existing register which is having a value of 5, and we are adding 100 to it. So 105 is getting added to it. So right now R1 is having a value of 105. Now we are storing back this result into a variable called result. So you are taking the value from R1. It is works in the opposite direction. So R1, whatever value is there, it is going to get stored in result. Initially we said result is a full word and we didn't define it, so we didn't initialize it. So there is a garbage there. So 105 is going and getting stored in the result. This is a very simplest snippet, but it will give you very important aspects. One, when we say AH, when we are adding a off word, you have to say AH. Similarly, when you are loading a full word, you have to say L. So let us look at some of these combinations below. LR or LGR. First, let us forget about the G part for a minute. Let us say LR. You are loading a register. That means copy from one register to another. LR R1, R2. That means from R2 you are getting into R1. Both are registers. Please remember this. Whenever you say LR, both has to be registers. You are taking the value from R2 and you putting in R1. LH, you are loading a offered, just like we saw earlier. AH, whenever you say offered, whenever you are doing offered related operations, you see the H there. Load a offered, and you are taking LH R1 num2. You are taking the off num2 is what variable? It is a offered. You are storing in the R1 register. Third one is L, load a full word. So we saw already R1 num1 is a full word. The full word is getting stored in a register called R1, and num1 is a full word. That is why we are using the instruction L. Now LG, every time when you are taking the value and storing in a you are taking a double word and storing it somewhere, you have to use LG. You will not see LG instruction many places in the old code, because this has come only when the GOS became 64-bit. Earlier it used to be called S360, 370, 390. We studied that all that hierarchy. Then it became GOS in year 2000. So at that time the 64-bit architecture came. So the double word is nothing but 8 bytes, 8 into 8, 64 bits. So wherever you are handling with 64-bit variables, you have to use LG. Okay, then two more variations of L we will see. Just L is said L R1 comma F100. Similarly, if you look at L R1 num1, they are looking same, right? Both the places I am using a L instruction only, and I am saying that R1 num1 and R1 equal to F100. What do you mean by equal to F100? Equal to F100 is a literal. So instead of I calling num1 defining somewhere and assigning a value of 100, I'm directly using the word L1 R1 comma F100. Second one, if you really look at last one, LHI, that means load immediate offered. So value that is there immediately next to it, to R1, that is getting stored. LHI R1 H80. 80, there is a offered, and LHI, so it is 80, value 80 is getting loaded into R1. Last two is very important. Let us understand. Many times we do the mistake here. When we say L R1 equal to F100, equal to F100 is a literal value. That means a memory gets allocated. Please remember, a memory gets allocated. It is not very different from R1 comma num1, where num1 is a variable which we are defining. We are assigning a address to it, and we are initializing a value. Here we are not using the num1, but we are saying R1 comma equal to F100. That means it is a literal, the value is 100, but a storage gets allocated somewhere in the system and at the time of compilation, and value is taken from there and it gets loaded into R1. Whereas when you say LHI R1 H80, it is a offered, the value is 80. There is no memory getting allocated anywhere. Okay, no memory getting allocated anywhere. The value 80 is directly getting loaded into register R1. Understand this particular difference. So let us look again. LR is register to register. LH is offer loading. L is a loading a full word. Please remember there is no LF. LG is loading a double word, and L when we can also use the L but with the immediate full word, but with a literal L R1 comma F100, and the last one we are seeing is LHI, so it is a off word. Directly the value is getting stored. In the both the last two cases, the value is already defined in the instruction itself, but when it comes to literal, the storage gets allocated somewhere, and when it comes to LHI instruction, that means there is no storage getting allocated anywhere. Just look one more time. If you are not clear, you can go through the same slide one more time. Thank you. Okay, so let us look at variations of the load. add and store, both for upward and immediate. Here, if you see, apart from the code, I have written something on the right side. This is nothing but object code. As I told, in HLASM, which is a high level assembler language, once you compile a program, just like any other programming language, you will get an object code. So what you are seeing in each of the statement, for example, LH R1 of 1. Okay, that is the assembler, high level assembler instruction. Whereas you are seeing 4810 C010, which is the assembler instructions object code. So how this works? Let us spend a minute. LH, we already know, load offered, where into a R1, which is a register 1, and off 1 is a variable, which is a off variable. So where is this off 1 defined? Below it is defined. Look at that, off 1 DCH 100. And here I said 000010. This is interesting. What is this we are talking about here? Off1 is a variable which we saw earlier also. We said it is a offered, which is a value is 100. As I said, when we compile this program, off1, a particular address gets allocated to it. In this case, let us assume it is the address is 000010. Actually, it is a displacement here. It is not the actual address, but let us assume for a minute it is the actual address. Then you define another variable called off2. So it left 2 bytes, 1011, and it went to 12, and off2 is defined, and it also got initialized with a value called -50. So if you ask where is the variable off1, you can say it is at a displacement of 00010 from the starting point of the program. Let us say you have the entire program, and we compile the entire program, and you start allocating address to each of the variables. What happens is that the variable, let us say often, got allocated a address called A010, but starting point of my program is A000. So what is the distance from the starting point of the program to this variable? 10. So it will say that I am sitting here at a address called 0010 from the starting point. Why we are getting into it? We read this concept of what is a base register. Base register could be one of those registers like 12, 13, 14, and so on. So let us assume that you are loading a program into a base register called R12. That means your starting point of your program's address is in the register 12. What does it mean? Let us assume the starting point of our program's address is 0. That means 0 gets loaded in the register 12, and off1 is a variable which is sitting at a distance of 0010 from the starting of your program. We have seen this. Similarly, off2 is sitting at a place 0012 from the starting of your program, and result is storing at a place 000B. Okay, so let us go back to the instruction LHR1 of 1. What is happening is that LH, the moment it says LH's opcode is defined as 48, so it puts a 48 there. Then R1, that is the two registers there. It is expecting two registers, but the first register is 1, second operand is a value. There is no register there. So what it has done is 10, and it said off 1. Where is this off 1? Off 1 is at a distance of 010, and from where it is, we said base register 12. 12 means if you go into hexadecimal, it is C. So from C, at a distance of 010, your off 1 is stored. That is what it is telling. It is telling that take the variable which is at a distance of 10, 010 from starting of the program, and the starting of the program is in the register 12, and load that value into a register called 1. And what kind of variable it is? It is a of word. So understand this. LH is getting converted into 48. R1, there is only one variable here. Second one is a no variable, so 1. And say in case of second register, it says 0 1 0. And what is the value? C, that is a register 12. And what is the distance? 0 1 0. Now let us look at the second one. We will understand this better. AH, what is we are doing? We are adding a value upward again in the register R1, which is already containing a value of 100 because we loaded it in the previous instruction, and we are adding a half 2. Half 2 is a minus 50. What is the opcode for AH? It is 4A. So the program will get converted into 4A. That means the moment the assembler instruction, assembler machine language, it says that 4A, oh, I am adding a of word here. That's what it will understand. So from English, we are getting converted into a object code. Again, R1, that means there is one register 1, and there's no second register here because second one is a variable. So we are saying 1 0. And of 2, where is the of 2 variable? It is at a C0 1 2. It is at a displacement of C0 1 2. Why we are using a displacement instead of using the absolute value of the address? This is something we studied when we talked about what are the base registers and why is the displacement and all those things we discussed. So of 2 is at a displacement of 0 1 2 from the starting point of the program, and the starting point of the program is in the register 12. So we are saying from C it is at a distance of 0 1 2. Then you are storing the value STH, storing the off word. From R1, you are getting into a variable called result. Okay, so STH, its opcode is 40. R1, again same thing, 10. And you saw below, result variable is stored at a distance of 0000B, or for time being understand that it is at an address called 000B. So what we are doing, C00B. So what is happening is that if you look at LH R1 of 1, each there are three parts to it. One is LH, whatever is the instruction LH, AH, STH, its equivalent opcode is coming. Then it is looking for two registers. In our case, I have only one register, so it is saying 10 10 10. And for second variable, second parameter, which is of 1, of 2, result, where is its address? It is telling me that this address is in so and so place. But how it is telling? It is telling that starting point of the register is loaded in the register 12. So I will stock it as C. From there, what is the displacement? Of 1 at of is at 10, of 2 is at 12, and the result is at a B. So it is showing those things. You will understand as we progress. Now look at next set of instructions, LHI R100. Think for a minute. LHI R100. So here LHI is again a instruction whose opcode is A7A. It has three values, unlike 48, 4A and 40. It has A7A. And how many registers are there? Only one register is there. So we are putting 1. So we are using that space A7 1A. And here see the interesting part, 100. The value of 100 is we have given directly. So it is nowhere sitting in the memory. So does it have address space? No, it doesn't have an address space. So the actual value itself is getting stored. So 0064. What is 0064? 0064 is hexadecimal equivalent of 100. So LHI is A7A, register 1 is 1, and actual value of 100, which is 0064. Now I'm adding a AHI. I'm adding the AHI. I means immediate. That means that second variable has to be either literal or it has to be a direct value itself. AHI, that means I'm adding a off word. Where I'm adding a off word to a register R1. What is the value of R1 right now? It is 100. What is the value I'm adding? Minus 5. So how does this get constructed? A7B, which is AHI, then 1 is first register, and value of minus 5 is FFFB. If you are not done hexadecimal arithmetics, it may look little confusing to you. But if you have done it, you will understand it. So practice it. Why -5 suddenly became FFFB? Okay, think over that. We have done a separate section for it, how we are converting the hexadecimals, how we are converting the decimal values into hexadecimal values. So AHI is A7B. There is one register which is 1, and value of -5 we are taking as it is, which is nothing but FFFB. Now LR R2 R1, that means what you are telling, copy the value of register 1 into register 2. LR is 18, okay, and there's no science behind this. There is no nothing to logical thing to think here. These are the instructions that is given by the IBM. If you can go and look in the book, LR is 18, R2 R1. Here for the first time we are seeing both the registers, register 2 and register 1. That is why you see 21. After that there is no variable side, so there is no address space, there is nothing to put here. So when you give a address, when you have a variable defined like of1, of2, it is stored somewhere in the address. So it is fetching the value from that particular address. That is why you see the address like C010, C012, C00B. Whereas when you give the value directly, it doesn't have to look for any address. So the value itself is converted and it is put in here in the instruction itself. With this knowledge, let us go to the third part. L R1 equal to F100. Interesting part. You remember equal to F100 is a literal, and when I said equal to F100, it is a full word and the value is 100, but it gets allocated a memory space. That is why if you look at L, you see 58 here, right? You see a 58 here, only one register. So 1, and then there is a 0 here, and value of 100 is stored at a distance of 0 to 0 from the base register C, which is a register 12. That is why you are seeing here C 0 to 0. Okay, so here is a memory. AFI, this is another instruction where you are adding a full word immediate. Here you are doing a AHI, you are doing a here AFI. So R1 again register 1 and -5 is the value. Interestingly, AFI is C2 9, C2 9, and register 1 and -5 is FF 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 FB. Okay, when same -5, when you said it is a off value I am adding, that means -5 is considered as a off word. That means the system is storing only 2 bytes. That means it is putting this as a FF and FB. Same -5, when you are saying it is a full word, it is putting into 4 bytes FF, FF, FF and FB. Both the cases, since it is a negative value, the value indicator of F, it is getting extended for all the bytes. So here you see 4 bytes and FF and FB, and here it's only 2 bytes. LR R2 R1 copy result to R2. Here again same thing, it is not different from this instruction, right? 18 is the LR, and from register 1 to register 2 it is coming, so it is 2 1. Think over for a minute. Every time when you are doing this, is what you have written in the program. This part, all this is what you have written in the program. This is what is getting generated as part of the object code. When we actually do the program and when we compile the program, we can see all this stuff. A couple of things to understand. First thing is, wherever every instruction has a particular opcode like 48.4, A40, etc. The second one is two values are the two registers. If there are two registers, it will use them. Sometimes the second one is used as an extension of the opcode if there are no registers there. It gets some cases it gets more complicated. Let's not go there. But for example, LHI is A7A, LHI is A7B, so on. The third one is the address. wherever there is an address like of 1 as an address of 0010, so we are saying C010. Instead of register 12 as your base register, let us just for the argument's sake say register 11 is your base register. You will see B here because 11 is a B. 010, right? You know this exact address 9, then A, B, C. So 11 is B, 12 is C. So if it is a B, then you will see a B, B, B here. So this is your base register plus displacement, that is this value. In case there is no address, we are given a direct values like 100, -5, etc. The value itself will come here, and if you give a literal, again address gets space gets allocated, so address of that value will come here. We will see some more instructions in the next slide. So continuing with our examples, if you look at here, we defined full one, full two, and result, and all are full words. So if you look at how it is stored, 0010, 0014, 0018. That means each variable is given 4 bytes. Why? Because it is a full word, it is given 4 bytes. That is why you are seeing 10 to 14 and 14 to 18. Now we are using these variables in our program. L R1 full one, we have seen this 58, which is L R1, that means 10. First one is a register 1 and there is a no register, so 10, and full one is told at C010. So it is at a displacement of 010 from the base register. Then we are adding it. If you really look at add, when we are doing the add, we are adding a negative value. There is nothing like a subtraction. So we are adding a negative value R1 full 2, which is at C014. Then ST we are storing back the result. Result is at 0018. R1 result. Initially we didn't define the value for the result, but when the result gets calculated, which is in this case is 50, it will get stored at 0018. Similarly, if you look at next example, full one, full two, full three variables we are using here, 100 minus 50, 200, and if you look at where they are stored at 14, 18, and 1C. So first L R1 full one, which is load 100, then add R1 full 2, then L R3 full 3. By now these are pretty clear what we are trying to do. 58 is load, A is 5A and 1 0. Then we are doing a load register. We are copying from R1 to R2. So LR is 18 and we are copying from 2 and 1. So register 1 to register 2 we are copying. That is why you are seeing 18, 21. You are not seeing any address there because this is all the register operation. Similarly, you have already added a value in register 3, which is 200. You are adding that to R2, AR, R2, R3. AR equivalent opcode is 1A. Then you are seeing R2, R3. So you are seeing 23. Again, this is a purely register based instruction. There is no address space involved. So this is a very nice way of looking into it. Whenever you are doing initial programming or whenever you are doing a debugging, you keep looking at object code. It starts giving you idea of how much storage is getting allocated, what opcode is getting used, which registers are in action. You keep coming to know about it. Understanding them will really help you. So we are trying to make this as a fully working program. Again, this is not the complete working program, but at least what we are seeing till now is this snippet. We are trying to add a few more stuff here and few more stuff in the end. The first one, if you look at, is a C-sect. You are seeing my prog1 C-sect and you are seeing and my prog1. So my prog1 is a program. It is called a C-sect, which is a control section. So when a program gets loaded into memory, the entire C-sect gets loaded. Okay, so understand that entire, whether it is a instructions, whether it is a data definitions, that is part of this particular C-sect, all gets
loaded into the memory space. A C-set contains executable instructions like what we are seeing here, LHST, or data definitions, and a addressable storage. That means that this storage variables are within the C-set. So when a program is loaded, the entire C set is placed into memory, and starting point of the execution is always the entry point, which generally happens to be the first statement. Now let us understand this. In this particular program, what we are seeing, there are variables num1, num2 result, and we are not accessing anything like an external file or external database. So all the data that this particular program needs is within this program. So your num1, num2 result, everything is already loaded along with the CSEC. So here there are two things that we need to understand: R mode and A mode. So what is A mode and what is R mode? As I was saying, the entire CSEC gets loaded in this particular area, okay, which we will come to it. What is R mode and what is A mode? Then in case what you need to do if you want to access something which is outside this storage space, that is where you look into the A mode. So R mode 24 means the program must be loaded within the 24-bit addressable memory, which is a 16 MB. But let us assume that the data you are trying to access is somewhere else, it is beyond the 16 MB. Then what will you do? First of all, why this problem came, or why this situation has come? If you really look at earlier, the addressable memory was for the S360 is S370 is the 24-bit. So your program and the address that you are accessing, everything is within the 24-bit. That means everything is within the 16 MB range. But over a period of time, the memory has moved from 24-bit to 32-bit. But your program is designed in such a way that it can still remain within the 16 MB or within the 24-bit memory only. Its instructions are like this, you can load it there. But I want to access something outside this 24-bit. That is why this new thing came, which is called A mode. A mode is addressable mode. My program is residing within the 24-bit, but my address can be remaining something within the 31-bit, which is broadly equivalent of the 2 GB. For let us say, let us try to understand this. Let us say you are staying in a place, and you said that okay, you can stay within this pin code or a zip code, but you are authorized to sell anywhere within, let us say, Bangalore city or a New York city, some or a Frankfurt, like that. So you are allowed to stay in this area, but you can go and sell in entire area. But let us assume that after selling it, at the end of the day, you have to come back to this place and you have to pay taxes, say in this particular pin code, in this particular municipality, you have to pay taxes. This is your jurisdiction. But you can go and sell anywhere, let us say in a certain range, which is a what is telling as a mode. And R mode means where you can stay. R mode could be 32-bit also, and A mode also can be 32-bit. But at any point of time, A mode cannot be less than the R mode, right? You can understand it. So R mode is 24, A mode has to be minimum 24, and anything about it. R mode is 32 or rather 31. A mode also can be 31 or it could be 64 also. In fact, when you say A mode is 64, it is a infinite. It's a quite a 5 EB, what we call it, exabytes we call it. It is a very huge space. And but remember this R mode and A mode, understand, maybe many times you don't have to change it at all. You don't have to even bother about it. Then we are saying using my prog1 or 15. What are you trying to say? Every time a program gets loaded into the memory, the starting point of the starting address of that particular program always goes and stays in register 15. Of course, we change it to register 12, that we will see in the subsequent programs. So it goes and stays in R15. So we are saying that anytime you are doing a calculation of the displacement, use the starting point as R. What are the address in the R15? Let me give a simple example. Let us say the starting address of this program that you loaded is A000. Okay, and a particular variable is at A0010. That means the distance from the starting point is 010. If it happens to be, let us say, R12, which is the base register, here we are showing R15, which is a default base register, but let us say we are saying R12, register 12 as your base register. 12 is nothing but C. So we say this particular variable at a distance of C012. C is your starting address, which is A000, and 012 is your displacement. So this particular variable as at C012. That means I'm telling my starting point and I'm telling a distance. Let us say I'm staying in say Raleigh City. I am using my Raleigh city. Let us say I'm using a Google Maps and I'm at a particular point. Google Maps will say this particular place is X distance. Atlanta is this far from you, or Washington is this far from you, or Florida is this far from you. So where you are put up right now, let us say you call it base register. Then you are going to measure a displacement, saying from this, if I have to go to Washington, this much distance I have to go. From here, I want to go to, let us say, Atlanta, I have to go to this much distance. That is the displacement. The, the place where you are right now, where your phone is there right now, we consider that as a 0 point. That 0 point happened to be, let us say, register 12. Then we say it is C, and C, from C, register 12, which is containing the starting address, is having a certain point. But if you really look into real world, every point, no point is 0, right? Every point has a latitude and a longitude. But you are telling my latitude and longitude right now is 0, assume, and measure the distance from that. Okay, I know it's looking little confusing, but we will keep talking this multiple times so you will get a better idea. Then we said BRR14. Since R14 contains a calling program address, BRR14 is returning back to original program coding. So address of this particular program, starting point of this particular program is at register 15. But let us assume this program is called by another program. Oh, where I am being called, that address is always put it in the register 14. So when the execution is over, when it has to go back, it should know where to go back, and that where to go back happened to be register 14 address. Not necessarily that it is always every program is called by some other program, but many times it happens that you are called from somewhere. Where I am called from is in register 14. And let us say you travel from Atlanta to Raleigh. Atlanta address is in R14. Your Raleigh address is in R15. And when you're done with your job, you have to go back to Atlanta. Let us say that is, you go back to R14. So R14 always contains the address of the calling program, and R15 contains the address of the current program. I hope this gives some clarity. Let's move on. Okay, so let's come back to our instructions. We are looking at all load and add in one place for easy understanding. First one, you look at LH, load offward, AH, SH. These all for the offwards, load, add, and subtract. So when we say offward, we always know it is 2 bytes. Then LHI, so you have a value immediately. It is not somewhere in the memory, but the value is there within the instruction. You are loading that value. Similarly, you are adding a offword AHI, and there is no SHI. It is a
negative value you need to add. Some, for example, if I want to subtract 100 from 200, then you say your register is already containing say 200, then you will say AHI, and you will say R1, and you will say minus 100. Instead of plus 100, you will say minus 100. That is the subtraction. So there is no separate instruction for the subtract sub the offered immediate. Next one is more important, LAS. Simple L, simple A, simple S. Okay, and load, add, and subtract. This is for the full word. Just remember, there's nothing like LF, AF, and SF. Just like we have LH, AH, and SH. It is just a plain L, A, and S, which is for the full word. Similarly, add full word immediate. Add full word immediate again. AFI. Again, there is no subtract full word immediate. Same logic we use. AFI, no subtract. It's yeah, no SFI, basically AFI only, but we just use the negative word. You might be asking, okay, then what is load immediate? Load full word immediate. There should have been some LFI. No, there is no LFI there. What you do, L, you say R1, and you use a literal, right? We have seen this equal to F100, something like that. We use a literal and we load the value. There is no load full word immediate, nor there is no subtract full word immediate. There's only one command, which is AFI. AFI can be used for addition, or with a negative value it can be used for subtraction. And if you are trying to load a immediate full word, then you use a literal. LR, AR, SR. The moment you see UR, you know that there is a register. So it has to be R3, R2, R1, R2, something like that. It is always a combination of two registers. It is not a value in the memory. Now, same commands after G system 360, which are S360, S370, we saw all that. Then after 2000, we have G came. When we came 64-bit, then the operation, if you want to use the 64-bit, then you have to use LGHI, AGHI, just like LHI, AHI. Yeah, when you say offered, the operation is still happening in the last 2 bytes, but the entire 64-bit is considered for the operation. But actual data is only in the last 2 bytes. Instead of A, you can have a AG. G is not, people call it grand, but in reality, there is nothing like a grand in IBM's literature, but for convenience, a lot of people call it AG, means a grand, which is nothing but a 64-bit. Then you have a LGFI. Interestingly, you have a LGFI. You don't have a LFI, but there is a LGFI. Then AGFI, it is nothing but AFI, but we are doing operation on 64-bit. Similarly, AGFI, no subtract is there. AGR, SGR, similar to AR and SR, again 64-bit operation. So last 4 lines is, you will see only programs after say 2000, when the 64-bit architecture got implemented, but most of the programs you deal today always having the instructions in first 5 6 lines, because most of this code is written in the earlier days like 60s, 70s, and 80s. You can have this slide as a reference slide. I will put this in the material. You can download it, and many times when we get some mistakes somewhere, most likely it is because of this particular reason. We are, for example, we are using say LFI, or sometimes we are trying to do SHI and the program is not working. Okay, let's move on. Okay, so it is time for some quiz. Let us test our knowledge. At each slide, I will ask the question. I will wait for 10-15 seconds. You also think, and then I will give the answer. Okay, don't cheat. Thank you. Okay, so what is this doing? L 10 comma equal to F100. What it does and what is the value stored. Okay, I hope you got the answer. Register
10 we have. In that we are loading, what we are loading? We are loading a full word. And what is the value of the full word? 100. And it is really not a load immediate, as we saw in previous slides. There's nothing like load immediate for a full word. The moment you say equal to F100, a memory gets allocated and value gets stored there. So essentially the system is picking the data from a particular memory location and it is loading in the register 10. So register 10 will have a value of 100. This is a instruction where you are doing a load, you are doing a full word, and you are using a literal, and literal in turn getting converted into a memory location where this value is stored and it is picking up from there. Okay. So what this will do, LHI 9 10,000. All right. So think over it for 5-10 seconds. I will come back. Okay. So let us break it. LHI. There are three different things here. L stands for load, H stands for half-word, I stands for immediate. So LHI is doing loading a half-word and it is saying immediate. That means the value is immediately next to it. So what is a register? Register is 9 and what is the value? Value is 10,000. The value 10,000 is getting loaded into register 9. Everything is perfect. There is no problem with this. Let us issue instead of LHI 9 10,000, you have done 9 40,000. What will happen? It will give an error because upward means it will go only up to 32,767. You have seen this before. It has a limit. So the moment you say 40,000, this instruction will not get executed. It will give an error. Right now we are saying LHI 9 10,000. So it is very much within the limit. So it is getting executed. Okay. So look at this LGR 8 10,000, right? Think for a second. What is happening? L is a load, G is a grant, that means it is working on a 64-bit register, and R is a register, and 8 10,000. Okay, got it? This is wrong. Why? The moment we say R, that means we are doing a register to register operation. So it has to be something like 8 9 or 8 10 or 11 10 or whatever it is. The combination both has to be registers, right? When you have a R in your instruction, both values has to be registers. Just think of it. You cannot have a value here. Okay, let's move on. So what about this? LGI 8 10,000. Looks good, right? We said that only 32,767 can only go into full word. Here it is a grand. So it is a 64-bit and technically there is no limit. Technically there is a limit, but there is a huge amount, huge number exabytes that can go in. Makes sense? Let us see. No, sorry, LGA don't exist. So either it has to be LGFI or LG HI. These are the small mistakes that will make an issue in the assembler program. Let's move, see next one. Okay, now let us look at this. LFI 10,000 comma 8 load full word immediate. So we are trying to load a full word which is already there in the instruction itself. Is it making sense? Will this work? Okay, let us see the answer. So this is a incorrect syntax. Why? The first operand has to be register. It has to be other way around. LFI 8 comma 10,000, not 10,000 comma 8. Here we are trying to load into a register called 10,000 the value 8. Naturally, that is not a right way of doing it. Right? There is no register called 10,000. Okay, let us look at this now. More interesting. LFI 11
80000. So what is that value? 800,000. And STY11F1. What is wrong here? The first part is we are putting spaces. So what the value you are looking at, let us say you are looking at 800,000, that is not coming here, only 8 is coming, so you shouldn't leave spaces like this. If you want to improve the readability, what you can do, you can put a small comment saying 1,800,000, 8 million, whatever the value you are trying to store, you can write that value in the comments. That will make it easier. You cannot put spaces like this. Let us assume that you have taken out the spaces and you put in the register 11 and you are storing that value into some variable called f1. So first of all, f1 has to be declared as a, this is not f5, okay, remember this is f1, it's a just name of a variable, and f1 has to be a full word. And what is y is a long storage. So what we are doing in a 32-bit store, it is a long address sty. When you say it is not your it is taking a 20-bit address space, so it is able to access much longer, much larger distance, and you are able to put the value 11 into f1. There's nothing wrong with it, only we are here trying to say what is y stands for, which is a long displacement. It is still using the 32-bit register. If you have to use the 64-bit register, you need to say stg. Okay, g is the 64-bit register, st is still 32-bit register, but instead of st, this is using a longer, a bigger address space. Okay, so sty is used for 20-bit address space. Here f1 has to be a double word. Okay, thank you. Okay, lhi load of value immediate in a register 10 and the value is 1 million. You are loading a million into a register 10 and you are taking that value and putting it a variable called f1. You are storing 10 f1. Okay, so does this work? Think for a second. Now looks like nothing is going to work, right? That's what it is looking like. So it doesn't work. Why? Because a offered can have only the maximum value of 32,767. So this will fail. LHI will fail. So what you need to do, you just need to load, but again in load there is no immediate. So what you need to do, you either use it as a literal or you put it in a particular variable and then you copy it. If you want to still load from an immediate value, you have to use a literal. Okay, let's move on.
Okay, AGHI 5 comma 100. So A standing for add, G is grand, so it is telling basically it is a 64-bit, H is a half word, and I is immediate. Anything wrong with this? Okay, let's look at it. What is 5? 5 is a register, so 5 register might be having a value and it is adding a 100 to that value. There is nothing wrong with it. This is all perfect. Only thing we need to understand is still you are adding a half word. So the range of a half word is 32,767 plus or minus, which we saw that. So irrespective of whether you are using a 64-bit or a 32-bit, the moment you are doing half-bit addition, you are sticking only to a value below 32,767. You cannot add a million here just because you are using a 64-bit register, because half word is still operating in those last 2 bytes. So the maximum value has to be still 32,767 only. This is perfect. Why we are showing this? To say that if you put a million here instead of 100, it will not work. Okay, let's move on. Okay, so we are seeing one more, AGFI 500. A stands for add, G is telling us that it is a 64-bit. We are operating on a 64-bit, but we are taking a full word add immediate. So what we are doing, we are taking a value of 100 and we are adding to register 5. if register 5 is already having a value of 4, it is making it 500. It is operating on a 64-bit, but it is just taking a full word. Okay, if you have noticed it, last three examples we are using a 64-bit registers, but remember that when we are doing an operation, we are doing it as a half word or a full word, like that. So only that many bytes will be affected, rest of the bytes will remain as it is. When we are saying that I have a place up to 64-bit, but the value I'm taking is just a half word, or the value I'm taking is a full word. You need to understand this. Why we are doing this? It is because there are a lot of programs already written, and maybe we are using those programs using that variables, but now we are operating with a 64-bit. That is the reason why this is happening. Okay, let's look at this. This is having more than one instruction. LHI 5 comma 5000. So load offered immediate. First thing we need to check whether the value will fit 32,767. Yes, it will fit. So 5000 will get loaded into register 5. But what we are doing interestingly, we are doing immediately SR 5 comma 5. What is SR 5 comma 5? You are subtracting register 5, whatever value in register 5, from 5. So what will happen if you subtract something from the same value? It will become 0. Even though I loaded 5000 earlier, since I have subtracted 5 from 5, now 5 value is becoming 0. And storing the same 5 into F1, that means you are storing what value you are storing in F1? You are basically storing a 0. So at the end of all this instruction, though you are initially loaded 5000, you subtracted the same value and you loaded back. So value is becoming 0. Okay, let's move on. Okay, so what we are doing here, again, three instructions. L 5 50,000, which is a full word, which we are loading into register 5, and we are adding the same value to register 5. So initially we have a 50,000, we are adding 50,000 to 50,000, and it is becoming 100,000. So now register 5 will contain 100,000, and we are storing this 100,000 into F1 register. All good. You can also use LGFI or LHFI instead of using a literal like equal to F50,000. So what will happen in that case? There is no memory will be allocated. The value gets loaded immediately. In case you are using a literal like this, then there will be a memory allocated and value gets picked up from there. Okay, let's move on. Okay, we have done that what we said in our previous slide. So we are doing a LGFI 50,000. Very good. AGR. So we are adding the same register 55. So whenever we are saying a G, basically we are using a 64-bit register, though the operation might be happening in last 2 bits or 4 bits, and we are storing the value back. Okay, so what we are doing, so ST5F1, but here is a small correction. Since we are using 64-bit for loading, 64-bit for adding, we should also use the corresponding command, corresponding instruction for storing back the value, which is STG. Okay, not ST. We have seen lot of examples. Okay, so let's move on. So in this training, we covered introduction to variables. How do we deal handling the integers? We are going to talk about characters, then we are going to talk about packed decimals, all these things in the later training classes. Here we restricted ourselves only to mostly for the integers. Then we looked into variations of add, load, and store. This will be very useful. We'll be doing it even you're going to multiplication, division. First thing is anyway we are going to load the variable and store the variable. So we are going to see this again and again. Then we have done making of an entire full program. We spent some time on what is a C sect, what is a mode, what is a R mode, and
how we are going to call, load a program, what is a base register, what is the distance from a base register, all these things we discussed, and we had a nice fun quiz. So hope you people have enjoyed this entire training. If you have made this far, you would have understood a lot in the assembler programming. We are going to have class 3 and 4 and 5 also, covering other topics like say characters, then you packet decimals, multiplication, division, a little bit on subtraction. Then how do we do a branching, jumping, all these things like any other programming language. We are going to cover rest of the sections. Hope you enjoyed it. And in case you need any training, you can contact us in the LinkedIn. Thank you.